So, what we're going to look at today is talking about your frame of reference or your point of view of where you are in relation to an object that moves, because that does make a difference. And we could spend lots of time on this, but we're just going to hit the basics. So, first of all, I've got my beanbag, and what I want to think about is the horizontal distance that the beanbag makes. Now, if I throw that up in the air, the horizontal distance that it moved is zero. It went up, it came down, and it landed in the same spot. Now, if I talk about the vertical distance, it went up, I don't know, maybe a meter and came back down another meter. The distance up, distance down was about 2 meters. The total displacement was zero. So once again, let's think about the beanbag and our point of reference. So first of all, if I throw it up in the air and it comes straight down, the horizontal distance didn't change. But what if I was moving as I did it? Here we go. So from my perspective, I threw it up, it came straight down. It didn't move. But if you were watching it from a different angle, you might have seen something different. So think about it. You drive in a car, maybe you took a car or a bus to school, and you got on the bus at your house and you arrived at school in the bus. In some senses, you didn't move. You are still in the same seat on the bus that you were when you left. But from your parents' perspective, they saw you drive away. So from their frame of reference, you moved. But from your frame of reference, you didn't move. If you're driving in a car, maybe moving down the highway at 100 kilometers per hour, you don't even notice that the car is moving sometimes because your frame of reference is really what's inside the car. Unless you're looking out the windows, you wouldn't even know that you're moving. I see that when I drive with my kids, and they easily fall asleep and they stay in their state of motion. They don't notice that we're moving unless maybe I brake. Maybe I have to stop at a set of lights or I accelerate to pass a car. As I change my speed, that's what they notice. It's the acceleration. Let me ask you this question. If you were moving at 1,000 kilometers per hour, at a steady speed of 1,000 kilometers per hour, do you think that you would feel it? What about if I suggested I could somehow make you travel at 100,000 kilometers an hour? Do you think that you would notice those speeds? Well, truth be told, you are moving at those speeds right now. You don't even recognize it because your frame of reference doesn't seem that you're even moving. Right now, our Earth is spinning on its axis and it rotates every day. And that here in the Halifax region is just over 1,000 kilometers per hour that we are rotating on our axis. We don't notice it because we're moving with the Earth. Likewise, the Earth is going around the sun at a crazy speed, nearly 100,000, actually more than 100,000 kilometers per hour. But once again, we're on the Earth as it moves. So our point of reference, we don't even notice it. So we've talked about if we were moving horizontally and what the point of reference is. So now let's talk about what about our vertical, our up-down? And the easiest thing really is to think of an elevator. So I went into our school elevator to see what happens and how that affects our motion. So what I did is I hung a mass from one of our Newton scales and I took one of our ring stands into the elevator here and I let it sit there. And what you'll notice is that just like it did in class, we could record the weight. But as the elevator started to move, the weight appears to change. This is called an apparent weight. So here's a beautiful picture of me in the school elevator. And let's say that I'm standing on a scale. So let's think about what kind of forces we have going on here. Well, we have a force of gravity that's pulling me down, and that always exists. And once again, that is my mass times 9.81 meters per second squared. And what we have is we have the floor of the elevator is actually pushing up on the scale. It's pushing up on the scale right here with the same force. Actually, maybe I'll make that a bit bigger of an arrow. We've got this equals force right here pushing up on the scale. Then what we have is we have the scale pushing up on me and me pushing down on the scale. So there's all kinds of things going on here. Okay? Now, the force of gravity and the normal force really don't change. What's going to change is how hard I'm pushing on the scale and how hard the scale is pushing on me. And what happens is that as the elevator starts to move, what we know from Newton's laws is that the movement must be caused by some kind of force. And if we have a change in the force, we must have some kind of net change in acceleration, because we know that the force is equal to the mass times the acceleration. So what we saw here is that acceleration changed. And what happens is the reading on the scale is going to change, because what happens is that how hard the scale pushes up on me or how hard I'm pushing down on the scale changes. And that is what we call the apparent weight. Now, remember, this is going to be either an increase or a decrease, and it depends upon the movement that's going on in the elevator. So we're going to look at each of those next. So let's think about how hard the scale is pushing against my feet. So first of all, if I'm in the elevator and the elevator is not moving, then my weight would be my normal weight, whatever the individual person weighs. If you weigh 100 kilograms, then it's 100 times 9.81. If the elevator is moving, but we're at a constant velocity, it's going at the same speed, there's no acceleration. So the weight would be normal as well. When the elevator is changing its acceleration is when things start to happen. And so what we are going to see, it's when the elevator starts and stops on either the up or the down motion. When you're going to go up, let's say from the first floor to the third floor, when the elevator starts, there's a sudden upward jerking of the motion. And what happens is that it pushes harder against your feet. And so what that means is that you have an apparent increase in your weight. When the elevator is stopping, that push disappears. And it appears that you have less weight, so it decreases. When you're going downward on the elevator, let's say you're in a high rise and you're going from the top floor to the bottom floor, it does the complete opposite. It goes decreasing at the start and increasing as you get close to the bottom. Because when the elevator is trying to stop, it's going to have a great push on your feet. Think about it for a second. If you were to stand on a table and jump off, what happens as your feet hit the floor? There's an increased pressure between your feet and the floor just for a moment. And that force is the apparent weight that you notice. Same thing in the elevator. Here is our first problem to solve. We have a 100 kilogram box in an elevator on the ground floor being delivered to the top floor. So I've put it on top of a scale here. And the elevator accelerates upwards at a rate of 3.2 meters per second squared. And when it's near the top floor, it's going to slow down. It's going to decelerate at a rate of 2.8 meters per second squared. And I want to know, what is the apparent weight at 4 different times during the trip? So before it moves, as it starts to go up, during the trip, and as it slows down at the top. Okay, and there's more than one way of solving this. So here I've got a 9-story apartment building. Here's the elevator sitting on the bottom floor. And we know that we have a force of gravity here, and it's 100 kilograms times the force of gravity. So it's going to have a downward force of 981 newtons. Okay, so that's the apparent weight before it moves. It's got a force of 981 newtons in a downward direction. Okay, so then what happens is that the elevator is going to start to move upwards. And as we apply this pressure, it's going to force these two surfaces together. And what happens is, as these forces get pushed together, we have an increased weight. Okay, so we have an increased weight there. Now, how much did it increase? And there's a couple different ways of doing this. What I'm going to do is I'm going to say, okay, well, we had an acceleration here of 3.2 meters per second squared. And we know that F is ma, so the force at that time of the acceleration is going to be equal to the mass of 100 times 3.2, which is going to give me a 320 Newton force. And so the apparent weight at this time, the F apparent, would be equal to 320 plus the 981 that we already had. And that'll give us 1,301 newtons. So that's the apparent weight as the elevator starts to move up. 1,301. Once the elevator gets up to speed, let's say it's here now, and it's traveling up, it's now at a constant speed. And when it's at this constant speed, there's no increased acceleration. It's just that force of gravity pushing down on that scale. So what's going to happen is that the apparent weight is just the force of gravity. There's no other forces acting on it other than that force of gravity. So the apparent weight is 981 newtons. Now, is that up or is it down? I'm going to say that it's in a downward motion, pushing on that scale. Okay. Likewise, right here, that was pushing down onto the scale. Or is it the weight of maybe the normal force pushing up on my feet? Okay, so then what happens is that this elevator continues to go, and it gets to about here, and it's slowing down. So it's still moving, but it's getting slower. Okay, so what we have here is we also have an acceleration, but this time it was a negative acceleration of 2.8 meters per second squared because it's slowing. As it's slowing, the floor doesn't push up quite as hard on the bottom. So what's going to happen is that we're going to have a change in the force. So once again, this acceleration here is going to have, force is mass times acceleration. So we have a negative 280 Newton force. So what's going to happen is that the total force will be our 981 take away 280. And that's going to give us a net force of 701 newtons when it's slowing down at the top. Once again, it's a downward push because it's an apparent weight.